How do photons work in quantum cryptography? Imagine sending a secret message that no one else can read, not even with the most powerful computers. That's the promise of quantum cryptography, and photons are the key players in making it happen. Photons are tiny particles of light, and they carry information in quantum cryptography. They are used in a process called quantum key distribution, which creates secure keys for encryption. In this process, each photon is prepared in a specific quantum state, like a certain polarization or spin. These states act like bits of information, similar to zeros and ones in regular computers, but with a twist. Because of the rules of quantum physics, these states are delicate and cannot be copied or measured without changing them. This is what makes quantum cryptography so secure. The sender encodes information onto individual photons by setting their quantum states, such as pointing their polarization in a certain direction. These photons then travel through optical fibers or free space to reach the receiver. If an eavesdropper tries to intercept the photons, they inevitably disturb their quantum states. This disturbance alerts the sender and receiver that someone is trying to listen in, so they can discard that data and try again. This security relies on the principle that measuring a quantum system always alters it, making eavesdropping detectable. For quantum cryptography to work well, the photon source must emit only one photon at a time. If multiple photons are sent in the same state, an eavesdropper could intercept one without being noticed. Researchers are working on advanced photon sources, like those based on defects in materials such as hexagonal boron nitride, to produce reliable single photons with controlled polarization. This helps keep the communication secure. Photons can also be entangled, meaning their quantum states are linked no matter how far apart they are. Entanglement allows for more complex and secure communication protocols, like quantum teleportation. However, photons can be lost or absorbed in the optical fibers used for transmission, which limits how far they can carry quantum information. To overcome this, scientists are developing quantum repeaters that connect shorter segments of entangled photons, extending the range of secure communication. In essence, photons in quantum cryptography act as tiny messengers carrying secure information through their quantum states. Their unique properties, like the impossibility of copying them and the fact that measurement changes their state, form the foundation of unbreakable encryption. This makes quantum cryptography a promising technology for future secure communication networks that are much safer than traditional methods.